Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So last time we took a look at an introduction to rendering. Definitely check that video out if you haven't already, because today we're going to continue off kind of where we left off in that video and actually talk about the architecture of this whole renderer and just the whole problem of we need to render graphics of the screen. How do we do that in an engine? As promised, I did prepare a little bit of a PowerPoint presentation, which should be pretty cool. So we're going to jump into that in just a second, but I just want to kind of start off by just saying, first of all, huge thank you to all of the patrons that make this series possible. Patreon.com/thecherno. Your support just means the world to me, especially right now because I'm so busy and I still want to be able to pump out these videos for you guys, and just seeing that people are so interested and supportive of this series is absolutely amazing to me. If you're interested in becoming a patron, definitely check out that link. You'll receive a bunch of rewards such as videos early, although that's kind of on hold at the moment since my life is so crazy. But you'll get access to things like source code for Hazel Engine that has already been like way written in advance, essentially. So this kind of stuff that we're covering now has somewhat been implemented already and is all usable in a branch, and just kind of as a way to kind of get more of like I guess more control into where Hazel is actually going, being able to steer it into the right direction. I commonly post things on Discord as well in the kind of patrons channel relating to Hazel's development as I write the code, and like it's almost like a development blog. At times I try and do that just to keep you guys updated with what I'm actually working on, because obviously I work on Hazel kind of independently, and then eventually what I kind of implement eventually way later in the future makes its way to videos such as this one. And obviously in these videos I explain what I'm doing a lot more and talk about like how we're going to structure certain things. Anyway, rendering architecture, let's dive in. Okay, so rendering architecture in the Hazel engine. First of all, that beautiful background is not rendered in Hazel. That's actually a photo I took in pretty much the south of Victoria here in Australia. If you want to see more of my photos, Instagram.com/thecherno, there'll be a link in the description, because I do love photography as well. But maybe one day we can render something like this in Hazel. That would be quite nice, quite a good goal to aim for. Anyway, there are two sides to this whole thing, and I guess one of the things that I should probably talk about, I mean, in the introduction to rendering video, I did cover a lot, and I don't want to really overlap too much, so we're going to be taking more of a practical approach at this now. But effectively, the way that I kind of see this is there are two sides to a rendering system in a game engine. There's something called the render API, which, again, this terminology is something that I've essentially made up. I mean, it does make sense, obviously, and other people have used it in the past and do use it, but this isn't like from some textbook or anything like that, so don't expect that. But essentially, what we have is a render API, which is the platform and API, render API, graphics API, specific part of this whole system that we're building. What that means is that this is actually specific to OpenGL, specific to Vulkan, specific to DirectX. This side of this line is stuff that we actually tie into those platforms or those APIs. Whereas this side, which we'll get into, kind of in the future once we get through all of these points, this is going to be like the render kind of the API platform independent kind of side of these two sides of this system. So let's take a look at what we've got. So render context, right? So again, this side, what this is it's an implementation that is implemented like in OpenGL or in Vulkan or those actual APIs. This is the stuff that is specific that we have to basically implement per API. There's no way around that, right? So we have essentially, what do we build, right? So we build a render context. We build things like a swap chain, a frame buffer, a vertex buffer. It might just be easier to just list all of these, I think, at once. An index buffer, texture kind of API, shader API, states, pipelines, render passes, and then we'll kind of move on to the next side. So let's talk about this for a bit. What I mean by this is that these are essentially, in a way, I guess you could call them render API primitives. And I've probably missed like a bunch of things. This is just like a loose kind of off the top of my head kind of list. But essentially we need to, if we're like, and the way that we're going to start this out, as you'll see in the next slide, is by implementing OpenGL. So if we use that as an example, right, what we need to do is essentially make, you could say a class for each of these things, but essentially an implementation for OpenGL for like this render context, this swap chain, this frame buffer, the vertex buffer, the index buffer, because these are kind of render primitives out of which we tell our graphics card what it is we want to do, right? So things like a vertex buffer, right? We have a buffer of data, we want to send it into the GPU, and then actually be able to use it maybe like kind of statically, maybe dynamically, however we want to use that, right? We need an API to be able to do that. And the cool thing about this is that we implement this in every API. So in other words, we'd have an implementation for OpenGL, we would have an implementation for Vulkan, right? And then once we have that, we can actually use it from the renderer side of things agnostically, right? Which means that it doesn't matter. We have one implementation of the renderer, which just says, okay, first up, create a render context and a swap chain. Then, create any frame buffers you might need for actual rendering. Then I want to render a triangle. So let's upload some vertex buffer data and some index buffer data. And we're going to create a shader, of course. And then we'll create a render pass or a pipeline or anything else we need. And then we'll kick off rendering that triangle, right? That's it. Okay. But the thing is, to render a triangle, we use this render API from the renderer. And the cool thing about this is that suddenly if we decide, well, actually, let's render using Vulkan or DirectX 12 or whatever, this part obviously is the part that contains the actual implementation of those APIs, but this part does not change. We just have to hit a switch that says, okay, now do it in DirectX 12. But our logic for drawing a triangle, our actual render commands that we pass in, are essentially going to be the same. Now, in the last video, in the introduction to rendering video, I talked about how it was really hard to kind of draw the line, and this is the line. This is the line I was talking about. I've drawn that line, and I've said this is on this side, this is on this side, right? But now you actually kind of see what actually belongs to each kind of side. Again, if I want to suddenly add a texture to a triangle, right? What do? Oh, I just say, okay, let's load a texture and bind it, and we'll draw using that texture, right? And we'll update the shader code, obviously, to actually sample from that texture and then draw those pixels. But how do we use that texture? We just say, oh, we want to make a texture, right? The implementation details of, okay, what does it even mean? I want to make a texture. Am I going to read that from a file? And then what am I going to do with that data, right? Is that going to be implemented via DirectX 12 or Vulkan or OpenGL or whatever? That is on this side of the line, right? So this is just an API that provides us access to that kind of lower level code, but then we use this API in our renderer to actually render what we want, okay? And the benefit of that obviously is that it doesn't matter what API we use under the hood. It's kind of like we're creating another API on top of all those other APIs that's going to do exactly what we want in a much, much, much simpler way usually. And then all the hard work is kind of done behind the scenes, right? That's kind of the whole idea. So let's take a look at things that the renderer would be responsible for. So the actual 2D and 3D renderer, right? Whether that be forward, deferred, whatever, that is going to be implemented largely using actual kind of primitives from this. Now, I have to mention that there are differences in the API. Like I didn't just say last episode that, oh, this is going to be so hard. It's always so hard to do this. And then here I'm like, it's easy. We're just going to list all, I'm going to list all these dot points. We're going to do this and that. Everything's going to be sweet. No, because, implementing a deferred renderer in OpenGL versus something like Vulkan, it's different. Because in Vulkan, you just have kind of more of these primitives than you do in OpenGL. In OpenGL, you just kind of create like a bunch of frame buffers and that's kind of it. Whereas in Vulkan, you can have like things like pipelines and like descriptor sets and just more kind of, just more actual content for this, which is why something like I count OpenGL as something completely different to like Vulkan or DirectX 12 because it is. Right? Like the approach to some of these advanced rendering techniques is actually quite different. So it's going to be interesting when we get into things like deferred rendering or even like tile-based rendering or anything like that, right? Because the way that we kind of set this up might actually differ, and we might have to extend this render API and basically, whenever we need to just write more Vulkan code than otherwise possible with these primitives because we want a more efficient way of deferred rendering, for example, because you can achieve deferred rendering with these primitives, that's fine, but Vulkan might have a better way of doing it by using like more control essentially. And obviously Vulkan has things like, synchronization primitives like fences and semaphores and that kind of stuff, right? Not something that OpenGL really has. So there's going to be some difference. It's not going to be as straightforward as this might look. Because I don't want you guys to think that I've made it out to be so hard in the last episode, and then suddenly I'm just like, it's going to be easy. It's not going to be easy. I'm just simplifying it for you guys so that we can actually start doing this, and so that you don't feel too overwhelmed, but maybe feel a little bit overwhelmed, just because I don't want to like make this out to be actually more simple than it is. So because of that, yeah, like we might have to say, well, you know what, it doesn't make sense to have a deferred renderer implemented with just these like platform and API agnostic primitives. That might not make any sense, and that's totally fine, because then what we'll do is we'll move that part of the code into the render API zone. Now the downside, the drawback, usually what happens when you make that decision is things get more efficient, but you suddenly have more code. Because suddenly, anything you move obviously into the render API zone needs to be implemented per API. So we need to suddenly have a deferred rendering or whatever implementation for OpenGL, for Vulkan, for whatever APIs we actually choose to support, which we kind of want to avoid, obviously. What we actually want to do is try and have as much code as possible in that platform and API agnostic kind of section of our code, because that means that we don't have to have a separate implementation every time we want to do that. The reason we have this line in general, this might seem like a silly question, but I know some people might be a little bit confused. The reason why we have this line is because, again, think back to rendering a triangle. Do we want to write code 4 or 5 times per API if we have like DirectX 12, if we have Vulkan, if we have OpenGL, if we have Metal, whatever? Do we want to write code to render a triangle for each API? No. What we want to do is create all of these primitives, and then, as I kind of described, we'll create a vertex buffer, an index buffer, and a texture, shader, whatever we need. We create that, and then like the code to draw a triangle is just easily handled by Hazel, right? And then that kind of branches off into all those APIs, so that we really only need to write that code once. If we want to render a triangle, this is the code to render a triangle. We write it once, and then it kind of will eventually lower and lower level as it kind of goes down into the API. It will eventually hit whatever render API we're using, such as OpenGL or DirectX 12. Anyway, let's get back into this renderer thing. So things like a scene graph, right? Like a scene manager. That's not something you usually have in. You don't want to write raw OpenGL code kind of in that, like for that kind of system. It's something that is, it doesn't have anything to do with actual rendering APIs. You have like sorting, right? Deciding what to render when, right? Some things might need to be rendered after certain other things because of things like blending. But also we typically want to be able to sort things that use the same material or the same shader or the same texture kind of together, so that we don't need to switch states as often. Things like culling, right? So what fits into our frustum, maybe some kind of occlusion culling as well. Those systems, again, have nothing to do with specific render APIs. We have to do them for every single render API. So why not just have, like, why not just have the renderer handle that, right? Materials. So materials are very closely tied with shaders. Essentially what a material is just a shader plus some uniform data. And from there, we'll probably have things like material instances, which are based on materials. That's typically how most renderers and most engines kind of work. But again, that's something that is implemented here. So having like client-side uniform storage and then a shader linked and all of that stuff, that applies to every single render API. That's not different. Whereas something like a texture or a vertex buffer, might be different per render API, which is why we need it to be here and not here, right? Hopefully this is making sense. LODs, right? Level of detail. So meshes that we have lower quality and like kind of smaller meshes essentially in terms of polygon count and triangle count. The further away we decide to render something so that we don't render as many triangles. Systems like that, not something that belongs in the actual render API. Animation as well. It's purely kind of like a client-side renderer implementation of that. Doesn't need any actual render API support. Cameras, right? Again, something that is just, we need to like, maybe a camera might be tied to a frame buffer, maybe a camera might be rendering to a render target, right? That kind of stuff implemented on the renderer side. Doesn't need to be part of that. In fact, render passes almost belong here as well. The reason I put them here is because they can be seen as a primitive, and they are implemented differently in different render APIs, but in general, if we want to control, like if we want to begin or end a render pass, again, there'll be an API for that in the actual renderer as well. visual effects, so things like particle systems, that stuff as well is... Now this stuff, don't get me wrong, will require support from Render API. Things I didn't list here are things like, batching, for example, or instancing, right? Batching is something that usually can be controlled by the render side, whereas instancing requires Render API support. So things like that, suddenly you decide you want to batch something, but you want to use instancing in this case, that requires instancing to be kind of set up in the API here, but then can be used from the renderer. So, that's something to think about as well. Post effects. And by that I mean specifically a post effects system, right? So actually, if you break down what post effects is, we render our scene to a frame buffer, and then we use a different shader to just render, a quad on the screen using a vertex buffer with kind of our post effects applied here. But also, for post effects, it's common that we might need additional data that we wouldn't need immediately. So for example, very simple post effects might be something like a color correction. That's easy because what do? We render our scene to a frame buffer, and then we render that frame buffer again using a different shader onto another quad, and then display that on our screen. And then that shader might do the color correction. Whereas if we want to do something like screen space ambient occlusion, right? Not a great effect, but let's just go with it. We need some other data from our original render pass, such as like position or normal data, right? We want those normals into like a separate buffer so we can then read them in our post effects shader, because we need that extra information that we didn't need before we ran that post effect. So things like that, right? So it does tie in together, and specifically I do mean as post effects system. The way that it might handle those render passes and those additional data that we need is something that typically would be implemented by the renderer, because this renderer just uses this API that we've created just so that it doesn't need to use OpenGL specifically or any actual render API specifically. I hope you guys know which render API I'm talking about. When I just say render API, sometimes I'm talking about this list, sometimes I'm talking about OpenGL, Vulkan, that kind of thing. But hopefully this is making sense. Other things. So I think, I guess render techniques like reflections, ambient occlusion, setting up reflections in terms of like reflection probes, rendering to like cube maps, doing things like ambient occlusion, whether that be in post effects or like kind of more advanced, HBAO or whatever other kind of render techniques we have available to us. Those things are typically implemented, in the renderer. That's something that we do there because we don't, sometimes we might need extra API support, but if you think about it, usually we should be able to get this API pretty strong to the point where we don't need to suddenly implement like finer grained things inside the actual render API every time we want to do like a different technique, right? Now, I do want to say though that the reason this has become difficult is because as nice as this might seem, like we can just have a render API, right? That seems great. Like we have a render API, we make it really strong, it handles everything. Suddenly, every time I want to do anything in my renderer, I have to write it once and it'll just work on every render API we support. That's a great dream to have, but in practice, that's usually not a very optimized way of doing things. The reason is that if you try and make a generalist render API, you have the same problems as if you try and make a generalist game engine, right? It's a game engine that can be used for any game any game you can think of, you can make with this game engine. But is that going to be better than if I write my own specific engine for my specific game? No, it's not going to be better, which is where this starts to become dangerous, because ideally speaking, like, if you get into advanced techniques that actually do require more performance, are you going to be able to write a generalist API and use that and receive the same level of performance and just optimization as you are if you just use raw DirectX 12 directly? Of course not, right? So you have to really be careful with this, and we'll kind of, as we go along, we'll kind of run into stuff like this and have probably some serious discussions, and may even like implement things one way and then be like, well, actually, this isn't as good as like this other test I did over the weekend and it turned out to be better, and we might go back on that. And I don't know, generally it should be pretty fun, but I'm just kind of warning you guys of some potential problems that will inevitably arise from stuff like this. Okay, so with that in mind, one of the things that I didn't mention, which we will also have to pretty much design, is essentially like a render command queue, right? And this kind of ties in like between the renderer telling the render API what to do, right? And a render command queue is just basically a way for us to encode every single render command into like a big buffer, so that once per frame, when we actually decide to like render everything, essentially, we go through that command queue and we execute all those commands. And typically the data is all inline. We can run it on a different thread if we want to, on like a dedicated render thread, so that while it's kind of going through that render queue, we could be doing other stuff like submitting more render commands for the next frame, or doing game logic, or doing AI, or anything else on our kind of main thread. So that's a render command queue. You know, an API like Vulkan has command queues, right? That's what you do in Vulkan. You have a bunch of commands, like for example, you know, bind this and then draw this triangle, and then, you know, this is my scissors state, this is my viewport state. And what you do is you put all of that into a queue, essentially. And then eventually you tell Vulkan, I want you to actually present that queue, right? I want you to actually go through that queue and then do that rendering thing. So Vulkan has that, but like OpenGL doesn't. So we need to create that for OpenGL. And, you know, just in general, if you have like a choice of like, okay, I want to implement 3 APIs, what do I make them like? Usually the choice is I'll make them like DirectX, right? Because DirectX, like for me at least, seems to be the most sensible actual API, right? So we might follow that kind of design, but because I like making new things and because Hazel is a new project for me, I might just try and make my own thing and we'll see what happens. And that's where we as a community, we kind of work together and we try and build something new and something cool. So just giving you guys a little bit of insight there. So where do we start? Talking is great, but we need to actually start this thing. So how are we going to do that? Well, first of all, we're going to start with OpenGL. Now, would I start with OpenGL if I was just making my own engine, like for fun, without making a video series out of it? Probably not. Probably wouldn't support OpenGL at all, to be honest. Just start with like Vulkan maybe. But the problem is, OpenGL is the simplest and the easiest API. It requires a bit of a stronger design from our side to make it actually good, but it's the simplest and easiest thing, right? We want that because this is a game engine series, not necessarily a graphics series. I am obviously heavily interested in graphics and I love graphics and it's my favorite part of this whole thing, to be honest. But I do recognize this is a game engine. We have kind of 2 goals. First of all, we want to see stuff on the screen as soon as possible and see beautiful things on the screen as soon as possible, because that's going to be great to actually see results. And obviously a lot of you guys actually want results because this is a YouTube series and it has to be fun in that case, and it has to be marketable from my point of view as well. I have to be able to make pretty thumbnails with like, hey, look, Hazel engine looks great. Even though, you know, if I chose something like Vulkan, the architecture might be amazing. We might have done a lot of code work, but do we have anything pretty to show? Not really. So there's that side. And then the other side is we don't want to spend 2 years implementing rendering APIs. We want to get something up and running and then move on to something else, like a scene system, or like a level editor like tool set, or like serialization and like data like that, or actual logic and scripting, or like an entity component system. We have so many other systems we need to deal with. So using OpenGL is not ideal, but it will get the job done, right? Not in the best way possible, not in the fastest way possible, but it will get the job done. So our step 1 with that is to build that render API part. So when I talked about this and all of these things, that's what we begin with. We build that stuff. Once we've done that, we build the other side, which is the renderer. Of course, these do have overlap. They're not dependent on each other, right? So for example, we don't need the render API to be complete before we can begin the renderer. Once we have enough in the render API to like draw a triangle, guess what we're going to do? We're going to write a renderer that can draw a triangle. Okay, so that we get that stuff up and running, and then we'll iterate over it and we'll add more things as we need them. You know, suddenly we want to be able to render to a texture or something like that. We'll add the frame buffer and the texture render target API at that point. Okay, after that, we have a base to render anything we want, right? And of course, by build renderer, I am talking about things like we need to build a material system, maybe like a shader parser, stuff like that. That'll be kind of included in step 2, essentially. But after that, we can render anything we want. You know, we want to render like some cool like PBR materials and like 3D models and all of that kind of stuff. We should be able to. So once we can do that, once in OpenGL, I can render like a full 3D scene that looks beautiful, right? With probably post effects and all of that stuff. That's when we're going to implement other APIs. Now, this is, and I did write to be decided because, as I said, we probably want to do things like a scene, you know, scene, level editor, serialization, all that other stuff I mentioned, entity component system, scripting, all of that stuff we probably want to do before we start diving into other APIs. But this is a series for you guys. If you guys decide that, you know, we've got enough stuff, let's just implement Vulkan, I really want to learn about that. if the majority of people decide that, I'm going to do that, right? I would love to do that, to be honest. But I'm just thinking about what the majority of people want, and obviously trying to make this series something that you guys enjoy and something that, like, especially like the patrons actually want to see. But not just patrons. Don't think that I only care about people who support me financially. Obviously I care about all of my viewers, but of course one of the perks of supporting me, I guess, is that you get to steer this series a little bit more into where you actually want. But yeah, so Vulkan, DirectX 11 and 12, Metal, that kind of stuff. That I will get to that eventually, but this is kind of the stuff I want first, right? We're going to start with the simplest API possible, and we're going to make something that looks pretty. And then after we have that, we can move on to other stuff if we kind of have the time and resources to do something like that. Okay, so that's pretty much it. Thanks for watching, guys. Hope you enjoyed this video. If you did, you can hit that like button. You can also help support the series on Patreon, as I've mentioned throughout this video. I do want to say that, like, this is a big journey. This is something that's going to take us a while. OpenGL is it's very simple in a lot of cases. It's also, because it's so simple, it can also be annoying in a lot of cases. But I think we're going to have a generally easy time with that, so I'm not too worried about the actual details about that kind of stuff. We should get something up and running pretty quickly, I would think. This is a good opportunity to check out my OpenGL series if you haven't already. There's a playlist of like 20, I think, or so videos that will kind of cover a lot of these primitives. I don't think I got I didn't get into like advanced things like frame buffers. Not that's particularly advanced, but I didn't get to things like that, I don't think, or, you know, render targets, or just like a lot of that kind of stuff. I probably will eventually in that series. I think what I'll do is I'll show an implementation of like, hey, you know, we need to write a frame buffer class in Hazel. Let's just do that. But then I'll link to an OpenGL series video that I'll make about frame buffers, where it actually talks about how frame buffers work in OpenGL. So I'll probably resume the OpenGL series a lot as we kind of move throughout this. Now next weekend, which is usually when I make videos, is my bachelor party, because as I mentioned in the previous video, I'm getting married in less than a month now. So because of that, I'm not going to be able to make a video next weekend. I hope you guys understand. I mean, if, you know, trying to balance my life and this full-time job and other stuff's going on, and it's just, my head's exploding. So this is, again, as I mentioned, a good time to go back and watch that OpenGL series, and maybe even try and implement a renderer yourself, right? Try and implement those things that I've outlined in the design, and then with that API that you've created that's OpenGL specific, or rather platform agnostic kind of, try and then use that API to actually draw a triangle. That's a really good place to start. Of course, you will be able to draw a triangle if you watch that OpenGL series. So that's kind of my homework and my, like, what I want you guys to do while I kind of have this break next week. And then we'll just get back into it. And to be honest, I'm really looking forward to it. So I hope you guys enjoyed this video, and I'll see you next time. Goodbye.